Now, to understand why some processes occur and some don't, we need to define reversible processes, and this will help us understand machines and how we can make them more efficient. Believe me, if GM tomorrow could come out with a 100-mile-per-gallon car, they would absolutely do it. And the reason they would do it is because they know that their competitors are going to figure it out someday, and they're going to do it too. You may not know this, but all manufacturers buy the competition's cars, take them apart, look through them, reverse engineer them, see what all they're doing, because nobody wants to fall behind in the race to build a better car. And it's not something that's illegal. I mean, it would be illegal for them to use the intellectual property that they gain from it that is patented, but the other way is you don't take the car apart, you just go read the patent, right? Now, sometimes trade secrets are used instead, where a company might discover something and they simply use it and put it in their product and don't bother patenting it, hoping that no one will find out about it and how it works. But I guarantee that everyone's looking at everyone else's designs. So if GM could make a 100-mile-per-gallon car that people actually wanted, they would do it. There are other problems, other difficulties, and to understand those difficulties, we need to understand reversible processes. The idea of a reversible process is it's something that can go forward and backward without any outside intervention, without leaving any trace that it has changed states and is back where it started on the environment. Now, these are things that actually don't exist. No process is 100% reversible. There's always some loss. Even the motion of the planets around the solar system, they're not reversible processes. They're close, and they're close enough that it's been going on for quite a while now, but reversible processes don't actually exist. But you can conceptualize them. If you've ever been to a science museum, normally at the entrance they'll have a clock, and it's this long swinging mass, or the swinging mass on a long tether to the ceiling of some type. And as the Earth rotates, the motion of this swinging pendulum changes and knocks over pegs or something to indicate that the time has changed. And it's really interesting to see, and you can imagine that those would be reversible, that they would just keep going forever, but actually what the staff will tell you is they have to usually start it about every day or so, or sometimes they'll have to give it another push throughout the day to keep it going, or several. But the idea of a reversible, frictionless, perfect pendulum would be that it goes to one side, and then it swings to the opposite side, and when it returns, in other words, when it completes its cycle, it's back exactly where it began. No loss whatsoever in its potential energy. As I said, unfortunately, that's not really the way these things work. You have to set them in motion each day for them to work. If you think about a grandfather clock, there's a pendulum that goes back and forth. Why does it keep rising to the same amount? Well, because you wind the spring, or you have a battery that's providing energy input. Really, the purpose of the pendulum is so that the swinging frequency is defined and keeps time properly. But we can imagine completely reversible processes, although they do not exist. They would produce the most work in work-producing devices, and they would consume the least in work-consuming devices. So your car would get better fuel economy, your refrigerator would take less electricity to run if they were actually reversible. And so you might look at this and say, well, you're claiming these don't exist. I'm not sure if I believe that, but if they don't exist, why on earth would we bother studying them? Well, the reason for studying them is because they will help us discover the limits of efficiency. What's the best that we can do in work-producing and consuming devices? There are plenty of examples of reversible processes. If we had a piston cylinder device with a compressed gas and we allowed that gas to very, very slowly expand in a reversible manner so that the work we got out would be equal to the work we have to put in to get it back where it started, that would be reversible. Unfortunately, there's no such thing. So this expansion would actually take eternity to accomplish. And of course there's going to be some friction on the sidewalls anyway, and friction immediately precludes a reversible process. So there are many things that can cause irreversibilities. Friction is the one that you and probably people on YouTube that are claiming they've made a free energy device is probably the one you think of first. In fact, in a lot of these videos you'll see them say, well, if I could just get all the friction out of this, it would take off and it would go faster and faster. That's actually not the case. The reason it's not the case is because friction is not the only irreversibility. We just had an example of a piston cylinder device. What if we allowed fast compression and fast expansion? What would happen? What would be wrong with that? I mean, it's just a gas after all. How come the work we put in would be different than the work we get out? Well, we can understand this by analogy. Imagine a dam with water behind it, where the water is just a static fluid. If you could move the dam, say to the right, so that the water level drops, well, then the net force applied to the dam would drop. And this is the way that compressed gases work, right? As the gas expands, the amount of pressure that it's applying does drop. So this is a good analogy to the piston cylinder device. As long as we don't move it very fast, as long as we move it very slowly, then you can imagine that the force on the gate is going to be as much as it could be from fluid statics, and the amount of work we would get out by allowing that gate to move to the right and the water level to drop would be equal to the amount of work we'd have to put in pushing the gate to the left in order to raise the water level and recompress the water. If instead we allow the gate or the dam to move very quickly, the water level near the gate is going to drop first. And if that's the case, then the amount of force that it applies to the gate will be less than if the water level were, just uniform across the top and level. And in fact, if we very quickly compress the water with the dam gate, then the water is going to pile up on the gate, and fluid statics dictates that the force will be higher, right? And so we'll be doing work against a force that is larger than the work producing force when the gate was going the other direction at the same position. In the same way, that's what happens in a piston cylinder device with a gas, because if you compress the gas quickly, the pressure in front of the gas is going to rise faster than the pressure at the other end of the container, just like the water level would rise faster. And if you allow fast expansion of the gases, you're going to have fairly high pressure gas at the cylinder head and not much pressure at the face of the piston if it moves too fast. And so just like the fast expansion, the moving of the gate to the right, as the water level drops, that's analogous to the pressure dropping on the face of the piston. So these are irreversibilities. I claim that the amount of work we put in during fast compression is less than the work we get out during fast expansion. And you can see that by the analogy in the water as well, because in the slow reversible process, the water remains very uniform, right? There's no energy, there's no motion of the water. But you can imagine that in case B, the fast motion of that gate is going to cause the water to slosh around. Even after the gate stops moving, the water is going to have some energy in it that was not used to push the gate. It's going to be some waste energy. And that energy will eventually dampen out because water does have viscosity. The water will eventually come to a uniform level. But where did all that energy go? Well, it went into warming up the water a little bit due to its viscosity. So this is a very good analogy to the fast expansion, fast compression of gases, and it is an irreversibility. It is something that reduces the efficiency below 100%, which we can't have 100% efficiency anyway, but it makes the efficiency worse because we're not getting as much out of it as we otherwise could. And this particular one has nothing to do with friction. So if we have unrestrained expansion of a gas, it's an irreversible process. By its very nature, that is an irreversibility. You can see the figure C there, the gas that had a membrane that's burst, and so the 700 kilopascal gas is rushing into the area that's only at 50 kilopascals. You could never reasonably expect all of that gas to be on one side at 700 kilopascals where you could simply repair the membrane or insert a new one, right? It just doesn't happen. That's one possible configuration, but in a practical time scale, that will never happen, right? Now, what about if you mix two gases together? Let's say you want to make air, okay? So you add oxygen and nitrogen, you mix them together, you're making air. Okay, great. Do you think they'd ever unmix on their own? No, you couldn't expect to put air in and one choose to go one way and the other one just choose to go the other. That's not the way this works. You have to put work in to separate the two. When I was in chemical engineering, we used a membrane separator that could actually do a little bit of separation of the nitrogen from the oxygen or vice versa. but we had to push the air through that membrane. Okay, you might think of many other ways. You might use cryogenic distillation, but that will require a significant energy input to separate them out. So these are irreversibilities. These are things that cause processes to be irreversible, and at their very core are things that reduce efficiency. If you have a gas that's trying to expand and push a piston, but there's friction along the sidewall of the piston, that's an irreversibility, because think about it. Let's say that gas starts off compressed, and you allow the gas to do work raising the piston. Well, which way did friction work? Well, friction required some of the energy, didn't it? Because not all of the expansion of the gas could be used for doing useful work. Some of it had to overcome friction. On the other hand, when I try to get that system back to where it started, I put boundary work into it, pushing the piston down. Now I'm working against friction, and not all of the work that I applied went into the gas and is stored there anymore. So friction was like the mobster, right? It got me on the way up and on the way down. It stole some energy. What it really did is it converted some work into heat, right? It converted work into thermal energy. You can do that easily by rubbing your hands together, but you would never expect warm hands to start moving your hands together like this, right? It's not the way it works. So friction converts work into thermal energy, and that's an irreversible thing. In the same way, heat flow itself is irreversible. If you have a cold soda sitting out on the counter and the surroundings are at 20 degrees, soda's at 5 degrees, you can expect that if you leave the soda out too long, it's going to be at 20 degrees, right? You would never expect to set out a 20 degrees Celsius can of soda and it naturally just drop down to 5 degrees by rejecting heat to the surrounding atmosphere, even if the surrounding atmosphere is at 20 degrees, right? That's impossible. Anytime there's heat transfer, that heat transfer is definitely an irreversible process. And all of these irreversible processes degrade the performance of our engineering systems. They cause efficiencies less than 100%. Another thing we need to define is an internally reversible process. So if we can't have totally reversible processes, are there some? Well, a totally reversible process would be something where we could transfer energy in, say via heat, but the temperature be exactly at the temperature of the surroundings, and so it's reversible. So again, there'd be no heat transfer. This would take forever, and this is a theoretical thing. So forget example A, right? That's not going to happen. What about an internally reversible process? Well, what if we had a saturated mixture of vapor and liquid at, say, 20 degrees Celsius, and we transfer thermal energy into the system? What's going to happen? Well, we'd have to have a reservoir at a temperature above 20 degrees, so let's say we've got one at 30 degrees. If we transfer heat in, some of the liquid is going to boil. Some is going to change phase from liquid into gas. Now let's just assume, for the sake of argument, that our piston has no friction, and I know that's a big one, but the piston's not the point in this discussion. Well, the piston's going to move up and do some boundary work, because it's has an atmosphere surrounding it, or maybe just the weight of the piston will be raised. It doesn't matter. Some boundary work will certainly come out of the system. Then let's say that we pull in a thermal energy reservoir at some temperature below 20 degrees and transfer heat out. Well, in that case, all that's going to happen internally is vapor is going to get into liquid, and work's going to come in. And if there's no friction, then the boundary work that comes in will be equal to the boundary work that left originally, and that would be an internally reversible process. So the boiling process and then condensing process were reversible, right? Now, it's not that the whole thing's reversible, because certainly there was heat transfer with the surroundings, so that eliminates this from consideration as a totally reversible process, but it's at least internally reversible. Internal to the system, the process completely reversed.